So when you think about acids and bases, something that you've probably heard of before is the pH. If you have a hot tub or a pool, you test the pH, and that is a measure of how acidic or basic something is. What we're talking about as describing acid and base and neutral solutions, and the hydrogen ion concentration, it's quite small numbers. You remembered how comparing the sizes, we were looking at scientific notation of very small numbers. So a pH scale is a much more convenient way to measure, and it's probably the more common way that you've heard of. So the pH scale is the parts hydrogen or the parts hydroxide or hydrogen potential, sometimes it's said. And so the key about this is that it's a logarithmic scale. So it's a base 10. Every time you move on the scale, it changes by a factor of 10. So each spot is times 10 on the scale. It's a lot like the metric system in that way. So let's just take a look at it. So it says, what is the pH when the hydrogen ion concentration is -12? And this image here in your notes is really handy. So the hydrogen ion concentration of -12 has the pH of 12. That's what we're talking about. It's talking about the exponent on base 10. So if I were to talk about answering this question, I would say that it has a pH equals 12. When the hydrogen ion concentration is 1 times 10 to the -12, the pH would be 12. That would be a relatively small hydrogen ion concentration. Do you see that -12? That negative exponent is really a big number, but that makes for a very small value of the hydrogen ion concentration. It also means that we're up in the basic category. So basic. Oh, not basis, basic. If I deviate just a little bit from the notes right here, what about neutral? So neutral has that ion concentration of 1.0 times 10 to the -7, which we talked about before, and that's a pH of 7. And so if we have a neutral compound, that's what our solution, that's what we're talking about. So this next question says, what's the pH when the hydrogen ion concentration is 1 times 0 times 10 to the -4? Or as it says here, just 10 to the -4, well, that gives me the pH of 4. So logarithmic scales are a way of talking about the exponent in a sense. So it's a relatively large hydrogen ion concentration, and it would make for an acidic substance. If you were to move, and like I said already on this one, how many times more acidic is a pH scale of 6 than 8? So you move 2 spaces on the pH scale. Each space was a 10 times difference. So we move from 6 to 8 or 8 to 6. 1, 2. Each one is 10 times different. So they kind of add on to each other. So 10 times 10 is 100 times different. So it's 100 times more different if you move on the pH scale 2 places. So calculating logarithms, and unless you've done a Math 12 course, you've probably never done the math of logarithms. So we have a button on our calculator, which is kind of handy. So if we know that there's a correlation between pH and hydrogen ion concentration, the log function on your calculator is a way of solving for the exponent. So a log means solving for exponent. And that isn't a massive oversimplification if you've done Chem 12 before, but for our purposes, it hopefully will work. When we take a look at this equation, we have a calculator button to do that. And so find the log button on your calculator, and we're going to practice putting that and using that on our calculator. As we practice using this equation, we also have something to keep in mind, and this is a bit of a weird oddity about sig figs for this chapter. So the way we remember it is the number of sig figs in the concentration determines not the sig figs in the pH, but the decimal places in the pH. And if you want to go into the reasoning behind this, I'm happy to chat about it. Most of the time, if you've not done logarithms before, you're happy just to remember the rule. So I won't go off on a tangent here. So the number of decimal places in the pH conversely gives you the sig figs in the hydrogen ion concentration. So I find that this is one that's a bit of an oddity. You won't lose marks in my course on sig figs here, but I will model this because if you're going on, the sig figs remain a convention in academic sciences. So in this one, if I'm solving for the pH, the equation is always going to be that pH is equal to the negative log of my hydrogen ion concentration. In this question, I know my hydrogen ion concentration, so pH would equal negative log of 1 times 10 to the negative 13. So you can just do that on your calculator. Hit the plus minus button, right? Remember the plus minus is different than subtraction. Then the log button. And then enter your number in scientific notation using that EE as for the times 10 value. When you do this, you should get a number on your calculator. Now, we have to remember how we're going to round. So the rules for rounding say that there's one sig fig here, so that means there's going to be one decimal place in my pH, right? That's what this rule is trying to talk about. So that means that I would have a pH of 13.0. So your calculator should have said 13, but when we use that convention of sig figs, we're going to represent that as 13.0. And concentration has molarity as the unit, but pH does not have a unit attached to it. If I were to say if this is acidic, basic, or neutral, a pH of 13 would make for a basic solution. So let's try these ones. We're going to practice this convention. We're going to practice using this equation in each case and the buttons on our calculator. So the pH here is going to be equal to the negative log of my hydrogen ion concentration. And so I don't have space to write the equation each time, but I'll write down what I would put into my calculator. So in this one, remembering the sig fig conventions, I have 2 sig figs in my concentration, so that means that I'd have 2 decimal places in my pH. So my calculator might say 1, but I'm going to represent the pH with sig figs as 1.002 decimal places because they had 2 sig figs in my concentration. And so again, if it's acidic, basic, or neutral, I've got a pH of 1. That's like hydrochloric acid. That would be acidic. You might notice a correlation here. When we just have 1 times 10 to the negative something, we really are just solving for the exponent or how many times we've moved the decimal place over. So this one, without using my calculator, I know that the pH is going to be 1, 2, 3, 4. So that's going to be a pH of 4. Let's check that with our way of using our calculator. So we'd want the negative log of this number. Sig figs, I would have 3 sig figs, so that's going to give me 3 decimal places in my pH. And so when I do this on my calculator, the pH is going to come out to, you guessed it, 4, but I'm going to write that as 4.000 as the pH. And a pH of 4 gives me acidic solution. So that's all fine and well as long as your concentration isn't anything but, to the power of 10, a 1 to the power of 10. That's not realistic. So these bottom ones here aren't going to be solved intuitively. You're going to need your calculator. And we're going to keep practicing using that equation. So pH is equal to the negative log of my hydrogen ion concentration. So that is what I would put into my calculator. When I put into my calculator that, I need to keep in mind how I do my rounding for sig figs. So I have 2 sig figs, so my answer would have 2 decimal places as pH. So 6.34 on my calculator. And if something has a pH of 6 or so, that would make it an acidic substance. The last ones, I'll write out what I put into my calculator. Give these ones a try, making sure your calculator is working for you. And then there's also that convention of sig figs where we've got 4 here, so that means I'm going to have, oh my goodness, 4 decimal places in my pH. So my calculator gives me, if I have a pH of over 7, that makes it ever so slightly basic. Last one on the page. You could write out the equation, or you could just write out what you're going to put into your calculator. The convention of rounding, I've got 3 sig figs, so my pH will have 3 decimal places, so 5.602 on my calculator. And if something has a pH of 5, that would make it acidic. So the next page is about going the other way. And again, if we have this understanding of this log button on our calculator and this basic understanding that it's solving for an exponent, you can go the other way. So if you know the hydrogen ion concentration, if you know the pH, you can calculate the hydrogen ion concentration. So mathematically, it would look something like this. For most of us, if you haven't done Math 12 before, your calculator, I'm going to solve for the hydrogen ion concentration by hitting the second function or inverse log. So that's 2 different buttons. It's the second function or inverse button and the log button, and then the plus minus button, and then the pH, whatever that is. So that would be my series of steps on my calculator. Sometimes I write out the formula as inverse log negative pH, which is inaccurate in the math world, but that's a handy way, INV, log negative pH. So again, let's practice with your calculator here. And this is going the other way. So the number of decimal places in the pH is going to give me the sig figs in the hydrogen ion concentration. So if I'm given the pH of 4, the hydrogen ion concentration, and this is my weird amalgamation of buttons I push on the calculator and the equation. So inverse log negative 4.0. That will give me a value, so I should turn my page, of, you can write it in sig figs or in scientific notation, or you can write in standard notation. I've got 1 decimal place here, so I'll have 1 sig fig in my answer. So 1 times 10 to the negative 4 moles per liter. So here, pH 11, I have 2 decimal places, so that means I'm going to have 2 sig figs in my answer. The equation that I write, it's the inverse log of negative 11.00. And so my hydrogen ion concentration to 2 sig figs is going to be 1.0 times 10 to the negative 11 moles per liter. The last one, not a nice neat number. We've got a little bit more going on. So I've got 3 decimal places. So that's going to give me 3 sig figs in my concentration. That's the rule on sig figs. The equation that I'm using is this inverse log or second function log, or you might have this button on your calculator here, that 10 to the x, or 10 with the arrow up. I'd put in negative 11.234. So my answer for this, my hydrogen ion concentration, is 3 sig figs 5.83 times 10 to the negative 12 moles per liter. Technically, you could do this straight into your calculator without showing your work, but I think it's handy, especially when you haven't studied logs, to kind of have a bit of series of buttons to push. So that is the pH scale. The pOH scale is kind of the reverse of that. So it's a measure of the hydroxide ions, and it runs opposite to the pH scale. The ways of calculating it are exactly the same, except for you're subbing in the other ion. And so in these ones, if I want to find the pOH, pOH is going to equal the negative log of my 2.3 times 10 to the negative 7. And your calculator can help you handle this. So I've got 2 sig figs in my hydroxide ion concentration, so my pOH is going to have 2 decimal places, or running that through my calculator, 6.64 on my pOH scale. So that means if I take a look at here, around 6, that would be basic on the pOH scale. So that's the way we do these. It's very similar to the others, so we don't have as many examples. It's negative log of 0.052. Running that through my calculator, I have 2 sig figs in my concentration, so that means my pOH is going to have 2 decimal places. And so my calculator tells me it's 1.28 on the pOH scale. So down here, between 1 and 2, that's going to be another basic solution. So going the other way, we've got a pOH given to us. So if I want to find the hydroxide ion concentration, that's going to be the inverse log or second function log of my negative pOH. So putting that into my calculator, knowing I have 2 sig figs in my pOH, means that my concentration is going to have, 2 decimal places in my pOH, means I'm going to have 2 sig figs in my answer. So I'd get 3.0 times 10 to the negative 4. And that would be another basic solution. The next one here, somehow I failed to do on my key. So I'll do this as quick as I can. Inverse log of negative 11.1. And now I have to fumble with my calculator. So second function log of negative 11.1. And remembering I've got one decimal place, so I'll have 1 sig fig in my answer here. So I'd have 8. Whoops, I forgot the units on there. 8 moles per liter. And when it is a pOH of 8, that would make an acidic solution. So last 2 here, or last 1 really. So what is the pH and the pOH of a solution with a hydrogen ion concentration of 1 times 10 to the negative 3 and a hydroxide concentration of 1 times 10 to the negative 11? So in this, if I multiply those two together, they do adhere to the Kw constant, right? You can't have an aqueous solution that doesn't. But this question is about the relationship between the pH and the pOH. They are the reverse of each other. So in this, and I'll give you the kind of punchline first, I'm terrible at telling jokes, pH and pOH, if you were to put those two scales together, those two would always add up to 14. So let's check this out. In this one, if I calculate the pH, it's the negative log of 1 times 10 to the negative 3, or a pH of 3. In this one, the pOH would be a negative log of 1 times 10 to the negative 11, or a pOH of 11. Well, these two, 3 and 11, do add up to 14. So for all aqueous solutions, because they adhere to the Kw concept, the constant of water, and we've got these two concepts of pH and pOH, that's the relationship between, the scale that you've probably heard of and the one that's new to us today.